This is the fourth major topic of foundation engineering. We only have one lecture for slope stability analysis. Actually, what we are going to do is that we will analyze the likelihood that landslides will occur in a slope. From a design perspective, we are trying to figure out the safety factor of a natural slope. If you have ever done any work relevant to slope stability analysis or read any materials about slope stability analysis, you may notice one thing, that is, for this topic, we have no man-made foundations in slope stability analysis. This could be a very common situation. So because of that, many people don't consider slope stability analysis and landslides as part of foundation engineering. But in this course, we do. And the reason is that we can view a natural slope as a natural system, like a foundation. And also, it is required to understand slope stability analysis and know how to do that before we can analyze the failures of many foundations. That is the deep shear failure that we mentioned before. Also, it is kind of common that people add some types of foundation to improve the stability of some slopes, such as piles, such as dewatering systems. So that's the reason we also include the slope stability analysis as one major topic of foundation engineering in this course. We have two objectives for this lecture. First, you will need to be able to explain the idea of a method called limit equilibrium method. Actually, there are multiple limit equilibrium methods for slope stability analysis. Second, you will be able to use a slope stability analysis computer program to calculate the safety factors of slope. After this lecture, I will show you guys how to use one typical program. So we will first talk about the limit equilibrium methods, and then I will very quickly went through two other major categories of slope stability analysis methods. Finally, we will have a demo to show how to use that computer program. Let's take a look at limit equilibrium methods. As mentioned, this is one category of methods. There are many of them, such as simplified Bishop, such as Spencer, such as Morgenstern. But here, I just show the general idea of it. So here in the name, we say the word limit equilibrium. The meaning is that if we have a slope like this, if we observe the landslide, we will see that usually we have a slip surface or failure surface. And that failure surface separates two soil bodies. Below it, the soil body does not move, but above it, the soil body will slip along that slip surface if a landslide happens. A typical slip surface looks like this. And one common assumption that we adopt for the shape of the slip surface is that in a 2D case, if we take a look at the cross section of the slope, it could be an arc, so part of a circle. So it's a part of a circle. That means we will have a center. And that's usually the case, especially for clay. But for sand, the situation could be much different from this. It's not that good. Let me redraw it. As mentioned, if landslide occurs, we will have the slope, something like this. For the liquid equilibrium methods, we assume that the soil body above the slip surface, that's this part, will move along the slip surface. And we assume that on the slip surface, all the material points, they will reach the critical state. Once a critical state, that means they reach this MC envelope. So every point is here, but they could have at different locations along this line. And because of that means that all the shear strength of the soil along this slip surface has been activated. And to do the analysis, what we usually do is that we need to divide this soil body above the slip surface into slices. Usually we assume that they have the same width. And we can take out any slice out and analyze. We know that the bottom is a arc, but if we assume that the width is small enough, we can use a straight line to approximate it. That's why we want to divide it into slices. If we don't do that, you have to deal with the arc. So if we have a shape like this, in order to get the safety factors, we want to take a look at the static equilibrium of this slice. So we have weight, and we may have forces from neighboring slices, and what is extremely critical is the stress at the bottom. So we also have friction, have normal force. And the idea of this liquid equilibrium analysis is that we assume that the force strength is activated. For example, here, if for clay, we would have the cohesion C sub U here, just like what we did before. We know everything, but if we sand or C5 material, we also need to consider friction. And so the strength relevant to friction angle will also be activated based on the magnitude of the normal force on the bottom boundary of this slice. So we have everything. We can get the forces acting on every slice. And if we put all of these forces together, and we know that many of them, such as the normal stress between neighboring slices, they can be canceled out. So eventually we can get an explicit equation for the safety factor. On top of it, we also have capacity. So capacity is the summation of all the forces that will help stabilize the slope. And we have loading, that is the summation of all the forces that will turn to fail the slope. So this is the idea of the liquid equilibrium methods. And you can see that there's a few steps. We need to define a slip surface. Usually we assume a slip surface. And the simplest case is that with a Potthoven circle. And then with the slip surface, we will divide the soil body above it into slices. And then we analyze the forces on each slice and put all the forces on different slices together, and we get the equation for safety factor. We can get the safety factor. But the problem is that we don't know what are the exact location of the slip surface. We don't know the shape of it. To do that, we need to try different possibilities. So to do that, if, for example, if it's a circle, we need to assume the center of it. So we need to assume XC and YC. We also need to assume the R. We try different combinations of XC, YC, and R values. And we choose the slip surface that can generate the lowest safety factor. And that lowest safety factor is the worst situation. And as we mentioned before, for design, we want to consider the worst situation. So the minimum safety factor would be the true safety factor. And for that purpose, for example, the center of the slip surface, what we do is that we first define a possible region for the center, and then we divide it into a grid. Then we try every point in the grid one by one, and we choose the one that can generate the lowest safety factor. Of course, for each grid number, we will also try different radii to see which radii will give the lowest safety factors. So this is the idea of the limit equilibrium methods. We still have other two categories of methods that you will also possibly see if you will be working on some slope stability analysis projects. One category of method is called the strength reduction method. Strength reduction methods, they are usually used with computer or numerical simulation. And in civil engineering, it's usually the finite element method. Actually, in geotech, finite difference method is also widely used. But no matter which numerical simulation method we are using, it's the same thing. What we do is that for slope, we want to analyze the stress and strain distribution inside it, and also we know the displacement. The idea of the strength reduction method is that we first assume the soil prop is C and phi, and we use pretty high values in C and phi, and we will not observe any issues here. But if we reduce C and phi, so this is original, and then we keep reduce C and phi, we know the soil will become weaker and weaker. At some specific point, the soil is so weak, so it cannot sustain the weight of soil body. So what's going to happen is that we will see a plastic region develop inside the soil body. If this plastic region passes through the whole soil, or some cases, the simulation cannot be continued because, the whole structure becomes unstable. If any of those conditions appear, then we record this C reduced and phi reduced. Then safety factor is the original parameters divided by the reduced parameters. So we know that it will be greater than 1. That's what we need. And many studies have been done to compare the accuracy of the strength reduction methods and the limit equilibrium methods. Usually they can give out pretty close predictions. The difference could be less than 5%. Another type of method, which is pretty old, is called limit analysis, not limit equilibrium analysis. And this one, these days, they're not widely used anymore. They are based on plasticity. So here I just give out some very basic information. And they will get something called an upper bound and lower bound. And also will give safety factors for these bounds. So these are the limit analysis, strength reduction methods, and the limit equilibrium methods. They are the three major categories of slope stability analysis methods that you will possibly see. And the most common one, of course, the limit equilibrium methods. such as Spencer's Morgenstern and Bishop Simplified. Last, let's take a look at one computer program. It's a demo. And I've already shared one program. It's called STB 2010. It's a very handy tool, pretty simple, and has very nice graphical user interface. So if you click the executable of that program, you will see this window. The use of it is pretty simple. So you can see that this shows you can change the name of it, but here I'll just quickly go through it. So if you click figure in the manual, you will see this is the default slope. So every time you start a new project, you have something like this. But this may not be the slope that you like. You can see that in the slope, you have different points to define the geometry, the slope. The soil is in yellow. But here we also have a line. Here's the line connecting point 7 and point 0 to define the water table. So groundwater can be considered, and even surface water. Here you can see that there's a water pound here. And also you can see here there's a region with 1.1234 as the 4 apices to define the possible region of the center of the slip surface. And we also have the slip surface here. So we can just click the calculation using this default slope to see what's going to happen. So if I click this calculator icon, and you can see that actually we loop over all the points inside the mesh for the possible center region. And eventually we end up here at this point. And this slip surface is the most dangerous one, and we get a safety factor of 1.977. And let's make a few changes. For example, we want to change the location of the water table to see what's going to happen. We can do it in different ways. One way we can do it that we can click this drag point bottom. You can see that there's a drag node. So if you click it, then you can move the location of any point. Let's move point 7 and point 0 and lower the water table a little bit. Each time we want to drag a point, we need to click the drag point bottom first. Let's move point 0. Let's make sure it's approximately horizontal. Before the drawdown of the water table, the safety factor is 1.977. Let's recalculate it. Oh, now you can see that the safety factor decreased. And the reason is that this surface water, the water pound, exert some hydrostatic force on the surface of the slope. That's the line between point 12 and point 3. If we lower down of the water table, we will reduce that hydrostatic force. That helps stabilize the slope, so the safety factor drops. But you may observe one thing, that is the most possible center is right on the boundary of this mesh. So that could mean that this point may not be the most possible center. The most possible center may be out of it. So to confirm that, let's enlarge this mesh a little bit. So we can also use the drag node function. I just do it in a very sloppy way just to show you guys the idea. Let's run it again. Point now is 1.730. Now if we change it, we get 0.731. That means the previous one actually is the worst situation. And we can keep changing the water table. Let's move the water table way below the slip surface. And you will see that safety factor increased again. The reason is that while the open surface water, they will help stabilize the slope due to the hydrostatic pressure on the slope surface. The groundwater, they will hurt the safety of the slope because they will create the buoyancy. So if we drop it to a depth that's far from the bottom of the slope surface, then all the soil is dry and strong. So because of that, the slope stability would increase again. And you may see that I just do it in a very sloppy way by dragging the points. We can also do it in a more accurate way by clicking nodes in the manual. And you can see the coordinates of all the nodes for both the soil, the water, and the mesh. And we can change the value, and in that way we can control different points accurately. And if you want to add more points, we can click this button here, this new node. You check it first. Oops. Check it first, then click any point. You can see that I just add a point 16 here. I can add another point next to it, and then we can drag the points to make a more complicated geometries for the slope. So that's how we can use a very simple slope stability analysis computer program. So please try this yourself. It's very handy if you want to get a quick estimate of the stability of a slope. Another thing that you may want to change is the soil property. So here this shows different soil properties that will affect the slope stability, and you can enter the values for the slope that you are trying to analyze.
I think I'm falling for you.